main points are summarized here. It does not have an absolute scale. It's an energy type quantity, and it does not have an absolute scale. Its numerical value, of course, depends on the reference state that we use for measuring energy. In electrostatics, for example, we use this convenient choice where all the at infinite separation, we say that the energy of that situation is 0, and we measure the energy. We measure the numerical value of that energy with respect to that reference state. I mean, this is important. I'll come back to this later when we talk about entropy. So if we also have this relation, so if you consider 1 mole of, I mean, all these quantities that we are going to be discussing, they're all extensive quantities. So you can always divide through by the number of moles in the system, and then arrive at the enthalpy per mole and entropy per mole and stuff like that. So you have this relation. So the change in enthalpy per mole of the system is given by Cp dt, where Cp is the specific heat capacity. Again, its units are energy per Kelvin per mole. And thermodynamics demands that it should be a positive quantity. If it is negative, then you can sort of think about horrible consequences that would follow, and sort of using the absurd consequences that would follow, you should be able to convince yourself that Cp should be a positive quantity, even from regular experience. But thermodynamics demands that it should be a positive quantity. Right. Next is entropy. So again, you are exploring some aspects of entropy in your modern physics course, and you probably have seen this earlier, but very colloquially, it is seen as a measure of disorder in the system. So one of the ways in which you can think of this is that a liquid form of an element has a higher entropy than its a solid crystalline form, because somehow we have this notion that in the crystal, the atoms do not really have much of a freedom, and therefore things are fixed and highly ordered and so on. Whereas in the liquid, atoms have lots of freedom to move about, and so the number of possibilities in which they can, the liquid form, atoms can organize themselves in the liquid form is way too high compared to what they can do in the crystalline form. So one thinks of liquid having a higher entropy. Entropy, unlike enthalpy, has an absolute scale, and so it is defined in macroscopic thermodynamics using the third law, and one says that it is its value is 0 for a perfectly crystalline element at 0 Kelvin. So, and then of course we also have this relation, which again comes from thermodynamics quite nicely. The change in entropy at constant pressure of a system of a mole of a material is given by Cp by T dt. Since Cp is a positive quantity, temperature is a positive quantity, and the entropy has a floor which is 0 at 0 Kelvin. So entropy therefore is always a positive quantity. So keep this in mind when we move forward. Okay, so let's now define something called Gibbs free energy, and its definition is for 1 mole of a material, it has this appearance. Okay, H minus Ts. And so it has the following features. At constant temperature and pressure, spontaneous processes are changes within the system. I mean, by this, we basically mean things that happen at constant temperature and pressure, such as and solidification of a supersaturated liquid and things like that. So the spontaneous processes or changes have the effect of decreasing the system's free energy. And so when all these processes come to an end, the system reaches equilibrium. So therefore, its G is at its minimum. So there are 2 ways in which the same statement is made. So Gibbs free energy G is minimized at equilibrium. So and another way of stating the same thing is that at a given temperature and pressure, one can imagine many possible phases or atomic configurations. or their combinations. And the one with the lowest free energy is the most stable at equilibrium. So we are going to make use of these statements in as we move along. So for the free energy, this is the definition of the free energy, H minus Ts, but gives you this expression del G is for a single phase system is minus S times dt plus volume times dP. So this is for a given phase. So we can write these things for all possible kinds of phases that we may have. All right, let's quickly run through the consequences for a single component system. So here is a set of schematic free energy versus temperature diagrams at constant pressure of, let us say, 1 atmosphere. So at a low temperature, solid is the most stable form. It has its lowest free energy, and liquid has a higher free energy, and the gas has an even higher free energy, and so on. So they all start at different values at low temperatures. And now let's talk about the slopes. All of them are sloping downwards, and that implies, in other words, their slopes are negative, and that's because del G del T is minus the entropy, and S is always positive. And the second feature is that all of them also become steeper as we go to, that is the slope, the magnitude of the slope becomes larger and larger as you go to higher and higher temperatures. And that's because of the fact that S keeps getting more and more positive at higher temperatures. So S at a higher temperature is higher than S at a lower temperature. Therefore, the slopes, the magnitude of these slopes must be even higher at higher temperatures. Because of that, they all have a negative curvature. And if you put both these facts together, then you realize that the red curve, since it is having a larger slope, which is also increasing in magnitude as you go to higher temperatures, would at some point overtake the curve for the solid at this temperature. And this is a temperature that we normally call as the boiling point. Similarly, the gas also overtakes instability beyond the boiling point. And so all of them, remember, have been drawn for one a particular pressure, let's say 1 atmospheric pressure. All right, so this then tells you that the solid is stable up to the melting temperature, and at the melting temperature, both the liquid and the solid have the same free energy, and therefore, if you think in terms of delta G going from liquid to solid, it is then 0. And between the melting temperature and the boiling temperature, liquid is the most stable form. And then beyond the boiling point, gas is the most stable form. And of course, we have seen all kinds of other complicated phase diagrams involving ice and iron and so on. So you can draw similar things at other pressures and then see what their stabilities might look like. So anyway, we want to look at the effect of pressure on this. So the way we do this is each of these curves moves up by the phase's volume times delta P if you increase the pressure by a small amount of delta P. And that's because del G del P is the volume, and volume by definition is positive. So all of them move up by a little. So since the molar volume is different for different phases, they will all move up different at different levels, and therefore they will the new curves that you draw at a higher pressure will intersect at other temperatures. So more importantly, the gas phase has a volume which is like 4 orders of magnitude or more higher than the volume of solid or liquid phases, and that is what we want to be looking at later. So we can, using these features, we can derive mathematically, algebraically, the relationship between the transformation temperature and pressure. So the way we do this is the following. So let's use these definitions at T1 and T2 be the transformation temperatures at P1 and P2 respectively. And so at both those pressures, at T1, P1, we have this relation because the two phases must have the same free energy. And at T2, P2, they also must have the same free energy. And therefore, the difference in the free energy of alpha as you go from T1, P1, the first state to the second state must be matched by the difference in free energy as you go from of beta as you go from the first state to the second state. And we want to convert this last equation into its infinitesimal form, where then we can deploy the laws of thermodynamics. So dg alpha therefore must be the same as dg beta for this alpha beta equilibrium, the two-phase equilibrium, two-phase coexistence. And therefore we have this equation. So you substitute for dg alpha from one of the earlier equations and dg beta, and we arrive at this relation, which is an important relation, which gives you the dependence of the transformation temperature, alpha to beta transformation temperature on pressure, and that is given by the change in volume of the phases, the change in entropy of the phases. So, and that yields very quickly certain interesting results. Qualitatively, the solid to liquid, if you look at the melting temperature, the delta V is of the order of cubic centimeter per mole. I will clean up these things and upload these slides once more. So this is about 1 cubic centimeter, rather 10 to the power minus 6 cubic meter. Whereas for liquid to gas, it is of this order, so at least 4 orders of magnitude higher. So that's on the numerator here. For elemental metals, take this as a given, but these are all empirically determined correlations. The delta S per mole for melting is of the order of 10 times the melting temperature, whereas delta S for, this should be liquid to vapor. So this is for boiling. This is of the order of 100 times the boiling temperature. Again, there is a mistake here. I'll clean up this and post it again. So you get this relation. So the bottom line is that the effect of pressure on boiling point is 1,000 times larger, at least larger than the effect of pressure on the melting point. The factor of 1,000 comes because you have this factor of 10,000 here and a factor of 10 here, and so putting them together, you get this really huge. More importantly, the melting curve in the phase diagram is essentially vertical when you look at it in the P versus T phase diagram, P on the y-axis and T on the x-axis phase diagram for a single component. So we can do a little bit more for the boiling temperature. Since the volume of the gas is many times, tens of thousands of times larger than the volume of the liquid, then we can approximate the delta V to the volume of the gas itself, and then assuming ideal gas behavior, we can replace this V sub G with RT by P. And similarly, the delta S, the change in entropy, is basically the latent heat of boiling divided by the boiling temperature. So putting both these things together, we arrive at this relation, which can be integrated quite easily. This is what we end up getting. So we see that the liquid gas coexistence curve has this relation, that is log of P when it is plotted against 1 over T would be linear, which is pretty nice, assuming that all these things are the constant. We are assuming that this is a constant. R, of course, is a constant, and T0 and P0 are reference pressure and temperature anyway. So because of that, you would expect this to be linear if the latent heat is a constant. And for many substances, this has been confirmed by and large, at least within the usual pressures that we normally encounter, not extremely high pressures. This delta H turns out to be constant, and because of that, you do get linear relationship between log P and 1 over T. Anyway, so I said 5 minutes, but I took about 10-15 minutes anyway. So I'll stop here and we will take questions. questions before we move to the binary diagram? Okay. Any questions? I mean, the reason why this is not there in Callister, the reason why I wanted to include this is to ensure that you don't leave with the impression that, I mean, the phase diagram is all sort of empirically determined. There is a strong theoretical basis for this, and that theoretical basis comes from thermodynamics, and that is important for you to see, at least at some level, in a quick and dirty fashion. Okay, any questions? Give some numerical problems involving these equations. We'll take questions now. Okay, since I don't see anybody raising their hand, I need to make sure that I'm audible. Can you all hear me?
Yes, sir.
Yes, sir.
Okay, cool. All right. So I thought I missed my connection, and you guys are maintaining strategic silence. Okay, then I'll move to the next set of slides, and then maybe we can come back and take more questions if you have any on this topic as well. But before we move forward, let's push all the quizzes related to. There will be, you can expect 2 quizzes on phase diagrams, both single component and 2 component phase diagrams, and we'll take them all up in one go next week. So which also implies that tomorrow we'll just have a lecture. We won't have a quiz tomorrow. So let's go to the next slide. Presentation.
Sir?
Yeah.
With respect to the homework problems, it'll be combined for like lecture 8 to lecture 9, right? Like, I mean.
That's correct. That's correct.
Okay.
Yeah. Because both the single component and 2 component phase diagrams are together in the text. They all appear in chapter 9, and there is a bit from chapter 10 that I will combine, which we'll come to tomorrow. So let's, yeah. So put together, we'll have one quiz maybe sometime on Tuesday. Okay. All right.
So tomorrow we'll be having a quiz, right?
No, we won't.
We won't. Okay.
Yeah, right. So the quizzes for both these sections, lecture 9 and lecture 8, that is last week's lectures and this week's lectures, will appear in a combined form next week, and preferably Tuesday, because that is the day that we decided we would run the quiz. And in between, I'll send you some questions that you can practice on.
Okay, sir.
All right.
And about the so the term paper also you'll be giving this week or next week?
No, I should have done it last week itself. It got delayed, but I will do it this week. So
okay, sir. Thank you.
Hopefully by Wednesday.
Okay, sir.
All right. So okay, so let me just move to the next. All right, these are binary systems. So again, phase diagrams, general boilerplate about what phase diagrams are. So they basically are diagrams in multi-dimensional space, and they divide that space into different regions, which we will be able to identify. Each region will tell you what phase is present, and if multiple phases are present, it will also tell you about what their compositions would be. Composition of each of those phases would be. So that's effectively what phase diagrams are. And so we are making next important leap here. So this leap is from one component to two components. The main difference is that in the one component system, for 1 mole of a component in the solid phase, there is no composition variable. So the entire solid is just 1 mole of that species. Whereas when we talk about the two different phases that exist, solid and liquid in an alloy, for example, then you can ask the question, what are the of those two phases? Solid in principle can have a composition which is different from the composition of the liquid. So, and that is the leap that we are making when we go from one component to two components. Since this is an introductory course, we would not really deal with the ternary and higher order phase diagrams. But at a later time, when you do materials and chemistry and stuff like that, you may get into those things as well. So, but before that, we need to get a hang of what a solid solution is. So you already have some idea about what a solution is. And our first encounter with a solution is in the context of dissolving some solid substance, such as salt or sugar, in a liquid, such as water. So colloquially, we say that solids dissolve in liquids. But on the other hand, you can also get a solution when you mix one liquid with another liquid. So here we use the word mix colloquially, but the end result is still a solution. So intuitively, we sense that the solution is one in which microscopically, if you take samples from different locations, would have a certain composition of the two constituents, and they would be identical if the solution itself is homogeneous. If the solution is not homogeneous, then the compositions would be non-identical. But at the atomic level, they are all completely mixed up. So in a homogeneous solution, samples, macroscopic samples that you take from different locations would have identical compositions. So since we use the word mix for liquids when they are in solution with other liquids, we also use the term miscible liquids. Those are that can mix in all proportions. Example would be water and alcohol, the kind of stuff that we are all now familiar with because of the sanitizer solutions that we get, that we use all the time. So it's a liquid solution of some alcohol. I believe it is isopropyl alcohol or something in water. So, and it must have, for it to be effective, it must have at least 70% alcohol and so on. So we also colloquially talk about mixture of gases, and there also it's also a gaseous solution, and atmospheric air is a solution of nitrogen and oxygen as the main components, but it also has a bunch of other things, including carbon dioxide, whose composition in atmospheric air is sort of going up, and that is a major worry for everyone because it has serious consequences on climate. Okay, so we also talk about immiscible liquids. These are liquids that do not form a solution, except in a very, very narrow range of compositions. For example, oil can dissolve only a little bit in water, but beyond a certain point, oil just separates out and then floats on top. And similarly, water also dissolves only a little bit in oil, and beyond a point, it just sinks to the bottom. So they don't mix. This is an everyday thing, and because of this, I mean, these words, immiscible and miscible, they have entered our vocabulary, mainly because we think of solutions being formed when liquids mix with other liquids, but they basically form a solution. And that idea is carried over to solid solutions as well. When you combine two solids, let's say copper and nickel, which is what we will look at later, they actually form a series of solid solutions right from the copper end to the nickel end. They mix in all proportions in the solid state as well. Okay, quick intro. So here is the water-sugar phase diagram, and it has this behavior. So the low temperature behavior is not fully captured here. There are some interesting things there. I understand. I like to look at some paper in chemistry that actually talks about the low temperature behavior. But we will also look at later water salt phase diagram, which also has a behavior, at least in the relevant part, which is similar to what this guy does. But here is our normal experience, room temperature to about a boiling point or so. And here it basically says that you form a solution when you dissolve. That means you are able to dissolve sucrose. The x-axis is in weight percent. So you can dissolve sugar up to a distance, up to an extent given by this curve here. Beyond that, whatever extra sugar that you add will simply sink to the bottom. And so that is effectively what this line says. It separates the state where you have two phases in equilibrium from the state where you have only one phase in equilibrium. So there are some interesting things that you can see here. This curve, which separates a single phase solution from the solution plus a crystal two-phase region, has this positive slope, which means at higher temperatures, you'll be able to dissolve a lot more. So given the phase diagram here, I see that at 80 degrees, at 80 degrees Celsius, 1 kilo of sugar will have as much as 800 grams of sucrose and 200 grams of water. But you bring it down to, let us say, 30 degrees Celsius, and it comes down to about 70%, which means 1 kilo would have about 700 grams. 1 kilo of solution will have can accommodate only 700 grams of sugar. That means you can go all the way up to the saturation level here and cool it down to 30 degrees Celsius. And then you can watch the sugar come out. One uses the term precipitation. It is a certain amount of sugar. By the way, this amount is wrong. Again, I'll clean up this. And if you do the calculation of the kind that we will introduce you to shortly, it will turn out that about 300 to 350 grams of sugar will actually precipitate out. And of course, since the sugar has a higher density, it will also sink to the bottom. So many crystal growth techniques basically use this principle. That means they dissolve a lot more of the crystalline substance in water, for example, at a higher temperature, and then you cool it down to lower temperature and just wait. In fact, these videos will also give you some indication of the time that is involved. People have to wait for days together to produce a nice crystal using a seed. By the way, this is also the method that is used for, I think you have seen the video of producing a single crystal silicon from the silicon melt. There it is from the silicon melt itself, but one uses the same idea of using a particular seed, a particularly oriented seed, and then you allow silicon to deposit itself onto this seed very, very slowly. There in that video also it said the process can take a couple of weeks. All right, so we have basically established a big chunk of whatever we want to talk about. So let's quickly go to a simple phase diagram. So because we are dealing with the two components, there is a composition variable that also enters the scene. And with the temperature and the pressure as the other variables, then these diagrams are basically three-dimensional in nature. And we take a constant pressure cut. So these are sections of this 3D phase diagram at a constant pressure where we can continue to use temperature and composition as the main variables. And this works for material science primarily because we are largely interested in liquids and solids. But chemists and chemical engineers are interested in liquid vapor equilibrium. Even they would use these 2D phase diagrams, 2D sections of the 3D phase diagram at constant pressure. But if they need information at higher pressures, they would take the appropriate cuts at those higher pressures and then use those as well. But there is a clear understanding that the phase diagram features would change quite significantly in liquid vapor equilibrium phase diagrams when you change the pressure. But in the case of solids and liquids, we just saw in the previous presentation that solid liquid equilibria are largely unaffected when you change the pressure. Okay, so with that understanding, let's jump into the first phase diagram that everybody starts with. This is the famous copper nickel phase diagram. And let's just go through the features. On the x-axis, you have the y-axis, you have the temperature, and on the x-axis here, one uses the weight fraction of nickel, right? Weight percent of nickel. This is basically weight fraction of nickel times 100. And of course, this is useful for industry people because if you say I need a solution, I need an alloy with 60% nickel, they simply weigh 600 grams of nickel and 400 grams of copper and mix them together and then melt. But in materials and in physical sciences largely, we deal with the atomic fraction, and that is also given here for convenience. But one can go from the atomic fraction to weight fraction quite readily using the atomic weights. And this is where I noted this. There is an error in this diagram. Since the atomic weights are different, they differ by about 10% or so. These two guys, these two scales cannot be the same. And there is an error here. Maybe we should point this out to Galister. Okay, so 0% corresponds, of course, to pure copper and 100% corresponds to nickel. So sometimes we simply leave these 0 and 100 out and we put copper here and we put all these numbers here and then replace 100 with nickel. That is the other feature. Okay, since the textbook also caters to the Americans, I suppose they also have given the temperature scale in Fahrenheit here. Okay, so we have, so at the copper end, pure copper, we know is an FCC solid at low temperatures and it melts at this temperature, and beyond that it exists in the form of liquid. And similarly for nickel, it is again FCC and it melts at this temperature 1453 degrees Celsius, and then beyond that it exists in the liquid form. At the melting temperature, both the solid and liquid coexist. And the other feature that I have to mention here, which I think comes in the following slide. So we get complete miscibility. That is, in the liquid state, both copper and nickel, they are miscible. They form a solution in all proportions. And similarly, they also form a solid solution in all proportions, which basically means that in the solid state, if you take the FCC crystal, then copper and nickel atoms are located at random on this lattice. You will be able to get a sense of what the effect is when you dissolve nickel in copper by, for example, doing, well, all kinds of experiments. One of the experiments that you can do readily is to measure the lattice parameter of the FCC crystal that results. And you will find that as you dissolve more and more nickel, the lattice parameter would change. I'm not very sure about which is a smaller atom here, but if nickel is a larger atom, then you will find that the lattice parameter would change continuously as you go from the copper-rich end to the nickel-rich end. Not quite linearly, it could change linearly as well, but we don't know much about the interactions between copper and nickel atoms. So in general, it could be nonlinear as well. The increase or decrease in the lattice parameter of the solution as you go from copper to nickel could be nonlinear as well. So you get all this stuff. So you have at low temperatures a continuous series of solid solutions. At high temperatures, you get a continuous series of solid solutions. Okay, in between, in the temperatures between 1083 and 1453, this is what we have. So we find that there is a lens-shaped feature in the phase diagram. So the top red curve separates the single liquid phase from the two phases solid and liquid region in the phase diagram, just like in the sugar plus water situation. And so that top curve is called the liquidus, well, he calls it line, but it is, as you can see, it is a curve. So it is a liquidus curve. And similarly, the bottom edge of the lens shaped region is the solidus curve, and that separates the two-phase solid plus liquid phase field or region, two-phase region in the phase diagram from the single solid phase region in the phase diagram, and that is called the solidus. So, I mean, these are the terms that we will use quite casually later on. So I think it's a good idea for you to the hang of it and not get confused when these words are mentioned in other contexts later. So it is quite clear that if you take an alloy such as something with let us say 80%, 60% nickel, this alloy. So as you keep heating the alloy, as you keep going up in temperature, it remains in a single solid phase with the same composition as the original alloy composition up to this point. And then you find that it enters a two-phase region and stays within that two-phase region up to certain other point. So, okay, in the example here, I've chosen 48% nickel. So let's take 48% nickel. So up to this point, that is about 1250. Okay, that is not quite correct. I made a mistake. I think never mind. So let's continue with this discussion. So this is about 1225 or so. Up to 1225, it remains in the solid phase, and between 1225 and let us say 1275 or so, it melts over this range. As you go to higher and higher temperatures, you get more and more liquid, and of course you reach this state having 100% liquid with the same composition as the alloy, and beyond the temperature, it stays in that liquid phase. All right. So these numbers are obviously wrong. I seem to have misread this. I don't know where exactly I took this stuff from, but anyway, I'll correct these things and repost this set of slides. Okay. Then therefore the question is, maybe I mistake. Okay. Anyway, never mind. So here is a situation where it is at 1250 degrees Celsius or so. If you take this alloy with approximately 35%, this is the alloy that we are talking about 35% nickel, and you take it to 1250, then you see that it is in the solid plus liquid region of the phase diagram. Then the question is, what are the compositions of the solid and liquid phases? Are they also the same as the alloy composition? That is 35% nickel. The answer is no. And this again has a solid thermodynamic basis, which we will try to give a hint of later in the next presentation. But the way, I mean, the mechanics of this calculation works in the following way. So what you do then is at 1250, you draw something called a tie line. And the tie line is basically the line segment at 1250, right from the liquidus to the solidus curve. So it is this line segment which is called the tie line, and the ends of the tie line then give you the compositions of the two phases. The liquidus end of the tie line gives you the composition of the liquid. The solidus end of this tie line gives you the solid composition. So we will stop here. Since I copy pasted the stuff, well, I copied the previous file and made changes here. I end up getting a whole bunch of things from the previous presentation, but we'll stop now. And we will come back and do some interesting calculations involving this and use certain arguments to find out what the implications are when you actually take an alloy and start from the liquid state. That is, you take it all the way into the liquid state and cool it slowly. And then what happens to the alloy as it forms the solid slowly. And we will talk about the grain structure, grain morphology a little bit, and also about the composition variations within the grain and so on and so forth. And we'll see the reasons for it. So, okay, we'll stop now. Any questions? Okay, I think some indication of the kind of things that you ought to know in terms of the terminology, that is just jargon, solidus, liquidus, tieline, and this and that. And also the key quantities here. There is alloy composition as well as the composition of the two phases that may coexist at some temperature in that alloy. And so on and so forth. Maybe that would be useful. I will send you that information in a separate document. So during the rest of the day, I'll clean up these slides and repost them at the same location. I'll remove the old slides. So you may want to take a look at the latest version a little later. So any questions?
Yes, sir. So like in a pure, in like a one-phase component, the melting at constant pressure, the melting occurs only at like, at one temperature, right?
Right.
So in binary thing, we just saw that it occurs over a range of temperatures, right?
Right.
So I didn't quite I'm not sure if I have the reasoning or no. Could you explain a bit more of that?
It is hidden in Gibbs phase rule.
Okay.
Did we explain that when we talked about the melting of a single component?
Yes, sir. In that.
Right. So there we said if you fix the pressure,
right,
then there is, and if you insist that two phases must coexist, there is no degree of freedom left. That means it must melt at one particular temperature if you fix the pressure.
Correct.
Right. Now you have one extra variable, composition. Right.
Right.
But you also have removed one variable, that is pressure has gone out of the window now.
Correct.
Okay. So this requires a little bit of thought. And so I will describe how exactly Gibbs phase rule applies to this situation. Okay. So the number of components has gone up from 1 to 2 now. The number of variables remains the same. That is, composition has entered as a new variable, but pressure has gone out as a variable because we are still dealing with a two-dimensional entity in temperature and composition. Right. So when you put this all together, you will find that an alloy now can melt over a range of temperatures at constant pressure. Two components. Yeah.
Also, like,
so you will get 1 degree of freedom.
Right. This makes sense. So also, like,
but it is applied in a particular way. So we will. But right now, there's a quick and dirty answer. It applies in a particular way. We'll look at those details in the next set of next presentation. Yeah, go on.
Yeah. So when I saw this binary diagram first, like 2 years ago, like when I looked at it, I think it is wrong, but just to confirm by the discussion, I know it's wrong. So essentially, what I thought was like, so now copper and zinc, right? So I thought first all the copper melts, and then after little bit of like, you know, after the temperature raises,
Right.
all the nickel melts and both of them are now liquid. So it's
Right.
wrong, right? I mean,
that is
just
that is clearly wrong. Yeah, because copper cannot melt at that temperature. Rather, okay, since you are at a temperature higher than. Okay, I mean, yeah, evidently it is wrong. We'll see some interesting counterexamples where the melting temperature here, the melting starts at a temperature between the two. Okay, let me turn the video on. So between the two melting temperatures, copper is lower and nickels is higher. So in this phase diagram, it is in between, right? The alloys start melting at a temperature in between these two extremes.
okay.
Later, we will see eutectic phase diagrams where the alloy can actually start melting at a temperature lower than both of them, the melting temperature of both of them. Okay.
Right.
So evidently that obviously cannot be correct, but yeah, you already realized it anyway. So I'm sort of belaboring the point here.
I just understood.
Right.
Okay. Thank you, sir.
Anything else? Okay, we are almost at 10:30 now. So if you want to move on to your next class, you can do that. But I will linger for about 5 minutes to see if there are any other questions.